Thank you, Vera, for the invite. Thank you all you guys for attending on a non-regular seminar day. I'll tell you a little bit of story about this, quick story. I met Bernardo Nipote, is an Italian, and we were in a conference, in a research week in Mexico, in Casa Matematica. It's a place where we gather researchers from different parts of the world. And his last name is Nipote, which is the same last name as mine, Nieto. So we said, okay, why don't we write a paper together? And say, that sounds good. And then we started discussing these ideas. It was 2021. And then we finished it 2 years later. Okay, so we had to invite the main worker of the paper, which is Ricardo. It was a student of him. We couldn't do it Nipote and Neto anymore, but it's okay. He practically did everything. So this is a story about stratification in survival analysis data. I come from a more theoretical world than applied, but in the end, I do have many applications. So I will concentrate in the applications. So I will go through the theory quickly. Okay. So these are only 3 points. I will concentrate on the results mainly, but I have to show the motivation and the model itself. All right, so I will start with the motivation. Thank you, Mandy.
Thank you.
Okay, so we have survival data, so we have times, and we have covariate information. And the idea is to propose a regression model and to do stratification analysis. So the most common regression model in survival data is the Cox proportional hazards model. And this basically says that there's a common hazard rate underlying for all individuals, which is called H naught. And there's a multiplicative effect of the covariates that modifies the hazard for each individual. There is another proposal of regression model. It's called accelerated life model. And I didn't find a better reference than this. It's a book. So I didn't find like a paper for this model. So I'm sorry about that. So I wanted to write this model in a comparable way as the proportional hazards. You don't usually see the accelerated failure time model written in this way, but I like it because we can see the difference with the proportional ones. So we also have a common hazard, but instead of only having the multiplicative effect outside, we change the time inside of the hazard. And that's the main difference between these 2 models. We know that there's one underlying common hazard rate that produces the same effect in both constructions, which is the Weibull. The Weibull constructions is proportional hazards and accelerated life at the same time. Okay, so those are the main 2, and there's a stratified version of the first one in the book of Kalflish and Prentice 2002. There is a stratified version of the proportional hazards model. And what is the difference? The difference is that we have strata defined by a discrete variable z. And for each strata, we have a different hazard. The covariate effect could be strata-specific, stratum-specific, or could be common to all strata. There's the 2 versions. But the important thing is that the hazard is different in each stratum. All right. So what I haven't seen in any book when I did my research is a stratified version of the accelerated life model. So I hadn't seen it anywhere in books. So I say, why not define a stratified version of the accelerated life model, just in the same fashion as in the proportional hazards. So we define a different hazard for a different stratum, and do an accelerated life construction. So basically what we're going to do is we are going to base our clustering and our modeling using the stratified version of the accelerated life model. Okay, so that's part of the objectives. What are the criticisms of the previous modelings? If I want to define these hazards for the different strata, for different stratums, I need to know a discrete variable that is going to define the groups. And the groups are usually defined a priori. So the question is, okay, why don't we define the groups a posteriori, if we do a Bayesian inference, and we take into account not only one discrete covariate, but a combination of different covariates, and these covariates could be continuous, could be discrete, and also based on the survival, observed survivals. So we define the strata posteriori, and once we have the strata defined, we do inference in each group. So we can estimate the hazard rate for each group in an accelerated like fashion. So that's the objective and that's the idea. And to solve the first problem, which is how to define the strata posteriori, we are using a Bayesian parametric mixture model. Bayesian parametric mixture models, they rely on a Bayesian parametric component, and this component is usually almost surely discrete. And because it's almost surely discrete, it allows for tags. And that's why these models are very useful for doing clustering. What are the models that are used for producing clustering in Bayesian parametrics? We have many options. One of them is the Dirichlet process, which is the most typical one. We have a two-parameter generalization of the Dirichlet process. It's called Pin-Major process or Poisson-Dirichlet process. It's the same thing. Another thing is the normalized random measures, which is an increasing additive process normalized, and stick breaking constructions. All of these are suitable for producing clusters. Because the normalized random measures are some models that were proposed mainly by Italians, and my two collaborators are Italians. They decided to use normalized random measures. So this is what we are going to use. Okay, but any of them would work. Sorry. So just one comment. Once we find the clustering using posterior inference, for each cluster we are going to do conditional inference on the clusters to have an idea of how the hazards behave for each group. All right, that's the objective. That's the overall setting for the proposal. Now, what is the framework we are going to follow? Okay, we are going to use the accelerated life model. And now we are using the main and the most common construction of the model, which is this. So we have an underlying time common to all individuals, and then we multiply or divide the time by a function of the covariance. And that leads us to a specific time for each individual. Okay, now, if we take logs for the times, so we can redefine the same model as a log linear model. So what we have is the log of the observed time, which is a linear function of covariates plus an intercept, and a function of an underlying log of the underlying T0. So this is basically a log linear model. And I'm going to be careful here that we have T0, Ti, Y0, Yi, and the difference between these four random variables is that the Y's, they have support in the real line, and the T's, they are positive support. Okay? Now, I'm going to use a an asterisk here to denote the survivals for the Ys, and no asterisk here to denote the survival for the times. So this is the survival for Ti, survival for T0, survival for Yi, survival for Y0. Okay? So we can rewrite the same model and define the survival for Ti in terms of the survival for Y0. And this is the definition here. The survival for Ti as a function of the survival for Y0, and we're just evaluating this inverse transformation. This is log of the survival time shifted by the location divided by the scale parameter. Okay, and that leads the survival for the observed time. Okay, in this construction, we have three parameters. Mu, the vector of theta, and the parameter psi. Okay, so what we're going to do is we're going to mix with respect to these three parameters. And we are going to assign a Bayesian nonparametric prior to these three parameters to produce the posterior cluster. So I keep going there because I want to shift with my hand. All right. Okay. So before going to the mixture model, we are going to define what the S0 functions we are going to be working with. There's three alternatives. We have the Taiwan minimum or the string value or the Campbell survival for random variable with real support. We have the logistic for Y0, has this survival form, and we have the normal distribution for Y0. Okay, so in these three cases, we have, in the first case, the Weibull, where we choose the extreme value for Y0. We have the log logistic, where we choose the logistic for Y0. And we have the log normal, where we use the normal for Y0. Okay, so these three are three different accelerated failure time models. Okay? Now, this is the general model. Okay, this general model is called model M2. And what we're going to do is going to propose a mixture model such that the log survival time conditionally on the parameters has this density. This density is the normal, the logistic, and the extreme value. Okay, for the parameters, the whole vector of parameters, mu, theta, and psi, we put all of them in the parameter gamma. So for the three components, we assign a normalized random measure. So conditionally on G, they are distributed as G, and the unknown random measure, it has a normalized form with three parameters. What is a normalized random measure? Normalized random measure is basically an increasingity process. An increasingity process is just a linear process that it has random locations with random jumps. And we accumulate those jumps and we normalize by the total mass. So that the form of the normalized form, it's a CDF. So that's called a normalized random measure, and it's a Bayesian nonparametric prior. This is defined by three parameters. The first parameter alpha is the total mass. The rho parameter determines the size of the jumps. It's called leading intensity. And the G0 determines the location of the jumps. Okay, so these guys, gammas, will have these locations, and the probability assigned to each of those locations is going to be driven by these two parameters, alpha and rho. This is how this measure is constructed. All right, so the important thing is that this measure is almost surely discrete. And because it's almost surely discrete, it allows for dies. And the gammas will not all be different, but they will be the same but different individuals. Now, for those individuals that have the same gamma, we will assign them to the same cluster. Okay, this is the reason behind model N2. Yes?
So, is rho a parameter or is it a function?
It's a parameter function. It's a parameter that we define that defines the model. It defines the level intensity, but it's a function. It's like G naught. G naught is another parameter, but it's a CDF. It's a probability distribution function. So the G naught could be, in this case, is a product of a minus 1 normal for this die and all of these dies, and an inverse gamma for this die. Because this is a precision parameter, this is regression coefficients, and this is the patience. So if I marginalize the normalized random measure, the marginal distribution for these guys, they will come from G0.
So does that rho S, it looks like an exponential function.
Yes, rho S is a function, and it's called level intensity measure. This level intensity measure determines the size of the jumps. This normalized random measure is a collection of random locations that are coming from G naught, and the random heights, they are determined by the random intensity, which is this function, and this total mass. We normalize this so that the jumps, they add up to 1, so that this G is a CDF, is a probability model, but it's random. It's a random probability distribution. Okay, this form of rho, of this function rho, that defines a specific normalized random measure. The normalized random measure is called normalized inverse Gaussian. There's different exponential forms, and actually this looks like a gamma. If you see here, it's a function of S. So this has a gamma exponent and a negative exponential exponent here. So it pretty much looks like a gamma. For different values of this exponent, we have other normalized measures. There's actually a collection, for instance, the stable process can be written in this form for a particular value of this exponent and this. The division process can be written with a particular rho function. Okay, but when we choose the exponent to be 3 caps, that gives to the normalized inverse Gaussian. So this is a very general construction. The general form of this rho is called generalized gamma. And this will be like a generalized random measure, normalized random measure. Okay. There's 2 simplifications of this model. What are these? The first one assumes that the effect of the coefficients, this theta I, is the same for all individuals. So this is one of the possibilities in the stratified proportional hazards model. When the only difference in the regression is that each individual has its own, each group has its own hazard, but the coefficients, they are the same for all groups. So this is model N1. These 2, they defined the hazard. Parameter mu1 and psi I, they define the hazard. And the thetas are the regression coefficients. Okay, so this is a simplification of our model. And a third simplification is when there's no covariate effect. So the difference in the individuals, so there's no regression. So theta is 0 means that there's no regression, and the theta, they come from 3 different hazards, which are going to be a function of this mu I and psi I. So no regression, common effect of the regression, and different effect in general for each individual. So there's 3 possibilities. Okay. Now, I will go quickly through here, just to explain what is the importance of this slide. when I assume that the gammas, they come from G, and G is a normalized random measure, that implies that the different gammas for each individual, they will be equal with positive probability. Because the measure is homogeneously discrete, so they can all, the different gammas, the different realizations from the measure, they can be the same. And whenever they are the same, I will assume that they come from the same cluster. Okay, now, how to choose the best partition? Each MCMC realization from the posterior distribution is a partition of the different individuals into different groups, different strata. How do I choose one of those as my best stratification? And that is called, this is why it's optimal. Okay, how to choose one from the many possible partitions that we have out from the MCMC. Okay, so one possibility is to follow a decision theoretic approach that was proposed by these two guys, Lloyd and Garamani. And what they basically do is they define a loss function for the one we are deciding with respect to the true one as the partition that minimizes this function. And this loss function has this form. It's called variation information loss function. It's just a loss function. That's the important thing. We are going to minimize the loss, and that's our optimal stratification. Is the one that minimizes the loss. Okay, this is the last theoretical slide, and then we'll move to data. Everything will be simulated, examples and data. Okay, there's a way of obtaining the posterior distribution from the normalized random measure, and that is characterized by this expression. The important thing is that usually the posterior distribution assumes that data is observed exactly. But whenever we deal with survival data, we know that the data can be right-censored. So the right censoring is going to be induced in the posterior by assuming a survival for the observation, for the censoring time. It will be censoring times, and then we consider this is the survival, the likelihood contribution for the censoring times. Okay. This is a form of the posterior, and we are going to do NCMC with this expression. Okay. Now, no more theoretical stuff. Now we are going to do a simulation study. Okay, I hope I'm clearly explaining the simulation part. Okay. So we assume that there's three groups. Parameter mu and psi, they determine the shape of the hazard. So we have three different shapes of the hazard functions, three different groups. Okay. And then we are going to choose the extreme value distribution so that the survival times they are Weibull. Okay, we are going to sample from this construction. Okay. Now, what is the effect of the covariate? We are going to consider the three cases. A first case, which is called P0, is data is coming, and where the data is coming from model P0, there is no covariate effect. So we are basically going to sample data from three different groups. Okay? We are assuming a different scenario, D1, when there is regression, and the regression is the same for the three groups, and the regression coefficient is minus 1.5. The covariate is going to be sampled from this normal 0.25. And the third scenario, D2, we are going to assume that there's a different regression coefficient for the three groups. For group 1, coefficient minus 1.5, as the one we had before, group 2, 1.6, and third group minus 0.1. So this is three different settings for each group. Okay. First one, so there's always three groups in the three scenarios. But in the first one, there's no covariate effect. In the second one, the covariate effect is the same. And in the third one, each group has a different covariate effect. That's the setting for the simulation. Okay. For each of the three settings, we are going to fit the three different models. M0 corresponds to data D0. M1 corresponds to data D1. And M2 corresponds to data D2. But we are going to fit the three models to the three data. So we are going to have 9 fittings. Okay? And we are going to consider three different sample sizes, 50 repetitions, and different degrees of censoring, from exact observations all to 30% of censoring, to see what is the effect of censoring. Okay. How are we going to define the goodness of fit of the model? So one thing is we are going to use the rank index. Do you know the rank index? No? Okay, we are going to measure the proportion of the well-classified observations. So in reality, they belong to these three different groups. And we are going to find a partition, a posterior partition, and they will be assigned to different groups. And we are going to measure the proportion of observations whose assignment coincides with the true one. So if this number is close to 1, that means that the posterior inference is doing a good job in obtaining the true clustering. Okay.
Can I question?
Yes.
What was the assumed form for the baseline hazard function here?
Okay, the baseline hazard is determined by choosing, it's basically a Weibull. The baseline hazard is a Weibull because we are using, this is, the density is the extreme value in the continuous scale, and that's defined by these three different parties. Collection of two parameters. Mu and gamma, mu and psi, they are the parameters that define the Weibull. Okay. This is the data before we show any results. So I love these graphs when I saw them for the first time. Okay, we have two different two rows of data. In this case, we have log survival times. And here we have the regression coefficient effects. Okay, in this scale, we can go back, values for the normal, the covariate. This is the covariate axis. This is the covariate axis. Here, there's no covariate inference. There's no covariate effect in the survivals. The covariate effect is constant. Okay? So actually, the covariate is on this side. I'm sorry, it's on this side. So we change the scale, sorry, the axis, so that we can project these values to here. So the covariate is the y-axis here. So this is a constant. Okay, so this group, these are the log survival times. They are only defined by three different hazard weights, three different survivals for these three groups. In this case, we have a linear effect for the covariate. That's why we know these straight lines. And each one has a different value. And we project the value to the survival time here, so we see this mixture. So this is the mixed data. We want to split the data into the three real groups. And you can see the effect of the covariate is the same. The slope here is the same. What is different is the ordinate. The ordinate is on this axis, and we have three different ordinates. But we have the same slope. The data is the same. Okay, here we have three different slopes. The blue, the red, and the yellow. And when we project the data, we have these observations. These are log survival, and they are coming from three different groups. These groups, they have different baseline hazards, and they have different coefficient effects. And we want to split them in the three real groups. But you can see this is challenging. Okay, so we are going to see whether the model is it's able to detect the different groups. Okay, and these are the results. Okay. Sorry. These are the 9 models. Across the columns, we have model model M1 and model M2. And across the rows, we have D0, scenario D0, scenario D1, scenario D2. In the main diagonal, we have the correct model applied to the correct data. Model M1 applied to data D1, and model M2 applied to data D2. Okay. So what we should be able to see here is that the correct model is doing good in detecting the values. We are seeing that model M0, they all have values close to 1. So we are detecting the 3 groups appropriately. Model M1 is detecting the 3 groups. But model M2 doesn't have values very close to 1. So these values are around 0.9. Okay, don't be misleading. This starts at 0.5. Okay, not that bad. Okay, so these values are 0.9. 0.9 is good enough, but don't be strict. 0.9 is very close to 1. All right. So, but they are not 1. The thing that we observe here is that these values are not 1. They are close, but not 1. Okay, another important thing that we see here is that if we fit model M0, so for scenario D0, and we fit the 3 different models, they are doing a good job for this data when there's no covariate effect. So with the 3 different models, we are detecting the 3 groups. When there is covariate effect, but the covariate effect is the same across the 3 groups, model M0 is not doing a good job because this assumes that there's no covariate effect. So this is a bad model. But the other 2 models, they are good. Okay? And here, the only good model is the correct model M2. And the other 2 are not doing that bad. You know, the range index is around 0.7. So 0.7 is not that bad, but the best one is given by the third model. But still not perfect. So this is not 1. Okay. Let's see another view for the same data. Okay. What do we have here? Okay. We have sensory. In the previous one, they were all exact observations. Here we have 30% of sensory. So what is the effect of sensory here? The correct model for the correct data, the rank index goes down to 0.8. So this difference between 0.8 and 1 is due to the 30% of sensory. So when we have sensory, we don't have full information, we are losing information, and even the correct model is not doing that good. For the second scenario, correct model has a value of the same, around 0.8. For the third scenario, instead of having 0.9 that we had before with no censoring, now we have around 0.75, between 75 and 80%. So we lose power to detect the groups when there's censoring present in the data.
Can I ask, so are you surprised the increase in sample size doesn't improve the RAND index?
Yeah, it's not the sample size here, it's the percentage of censoring. Increase sample size improves.
90, 150, 300?
Sorry. I'm sorry. Yes. Here, the 3 colors is different sample sizes. Yes. Here we have, so what, you know, the effect of the sample size, it's only in the size of the box plot. But it doesn't move the location. So it's not moving the location upwards. that we supposed to be. And this loss of information and loss of power in the groups is all due to censoring. Yes, that is surprising. So not even large data set. So we didn't try other data sizes. So we didn't try 500 or 1,000. We didn't try that.
I think it's a trade-off, right? Because if you have a larger N, the partition you want to learn has to be more difficult, right? You know, if you're partitioning 30 people versus you're partitioning 300, the second is much harder task. But if you have N equals 300, then you have more statistical information to potentially estimate the cluster. So it's a trade-off. A harder problem, if you increase N, but likely you still have some statistical information to estimate component-specific parameters. I think maybe that's reflected in the Monte Carlo structure there. Yeah, sorry, the error there.
So the rand index maybe isn't such a perfect measure here.
Exactly. So we're expecting an improvement, but we are not seeing that here in the random index.
Yeah, I usually use adjusted random index to correct that random chance. So there's an adjusted version which centers a 0 for chance agreement, and it is 1 going to be perfect agreement. And then clearly, most reasonable methods will give you a value between 0 and 1, but adjusted random index will be between -1 and 0. So I think, I don't know, maybe if you for different N, you may have different degrees of chance agreement. So perhaps that's going to reflect it.
So this measure can be improved. Yeah, thank you. Thank you. Yes.
So, did you try like the estimation of the individual, the hazards in the individual groups of the partitions? Like how good is the hazard?
Yes. That's the next slide.
Walk into that.
Okay, it is here. So how much is the survivals? So these are the different survivals. So these are the estimates from, okay, this is the two scenario. So the data is coming from the most complicated model, different coefficient effect for the different groups. And we are showing the fitting from model M0, M1, and M2. Here, the true hazards, they don't look, the true hazards are the dotted ones. They are not the same as the estimated ones. So they are different. In model M1, the hazards, they tend to be closer to the true ones, but here are the three ones. So this one is doing a better job. Still, there's a difference here, but it's doing a better job than the other two. And I don't remember if this is with censoring. What is the percentage of censoring in this graph? I forgot. I don't remember. Okay. So for this group, this red one is doing a very good job. The yellow one is not that good, and the blue one is the worst. But it's not that bad. Comparing the three fittings, this one is a lot better than the other two, but still not the best. Okay. Here is again, but now we are generating the data from 3 different scenarios, and we are analyzing the model M2. Okay. 3 different scenarios for the 3 rows, and we are fitting the data with model M2. So in the 3 cases, our fitting is not that bad, as compared to the true one. This is the true value for mu, and this is the true value for theta. Okay. There's 3 different values for mu, so the mu is very well estimated with the first 2 models, and here we are a little bit away from the true value. But for the value of theta, which is the regression coefficient, there's no effect here, so we are capturing that minus 1.5 common effect for the 3 groups. So we are capturing this, and the effect, the different effect for the 3 different groups, we are also capturing that in here. The only thing that we are not doing that good is in here, which is value of it. But the rest, we are doing okay.
Can I ask, so on the left-hand side, 3 graphs on the left-hand side.
Yes.
It looks like there's not really much overlap between the survival times in these graphs. I mean, there's
dotted lines are quite separated and there's almost no overlap, so that's sort of the timing is what's driving it.
Yes, but okay, the first times are of course very small, coming from the blue group as compared to the others, but there is still a little overlap. That's why we have the data when we have the log. So here they are very well separated when there's no covariate effect. But once there's covariate effect, they overlap.
Right, I'm sorry, there's not much overlap.
It is, we have those here on the right, in the middle we have the orange ones and the yellow ones. We also have yellow ones here, but we cannot see them. So you see, and it's a little bit, there's a little bit. Here's the most overlap one, and there's a little one here and no overlap here. Yeah, perhaps we could have put in a better scenario when these three they
Get rid of that one.
Oh, all right. Yeah, you could have got in a different scenario for this one, so they mix more. Yeah. Okay. And this is a real data analysis. It's a small one, just to illustrate that it doesn't work with real data. Okay, so we have 455 data points, 24% of censoring, and we are measuring return time to drop use. It's time to relapse in days. And we have two covariates, age and treatment duration. They are continuous both. They are both continuous covariates. And we have for our modeling too, we are putting a prior for tau. If you remember, tau is a parameter that drives the size of the jumps in the normalized random measure. So we are putting a prior for tau to become a 101. And we are fitting model M2. We are using the efficiency specifications, and then we try three different kernels here. By the way, in the simulation study, we use the appropriate kernel. We sampled from the stream value, and we use the stream value kernel. Here we are, because we don't know which kernel fits better, we are using the one that leads to the Weibull, the one that leads to the log logistic, and the log normal. According to the LPML, the best fitting is going by the one that leads to a Weibull hazard. All right, this is the data. This is the survival for the data. The largest values are censored, so the survival function doesn't go to 0. And we identified 5 different groups with this data. So perhaps we don't see, well, we can see like the modality here, but of course the sense observations we have to be taken into account. But we identified 5 different groups. Okay. This is the composition of the different groups. The first 3 groups, they don't have sensor observations, it's only exact. For groups 4 and 5, they have each of them 8 and 102 sensor observations. Group number 5, the majority of them are censored. Okay, and these are the 5 different groups. These are the exact observations in each of the groups. And this is the effect of age in the log survival, in the log time to relapse. Perhaps the scale is not the best, so we cannot see the effect. But in the numbers, we do. Okay. These are the 5 different survival curves. On the right-hand side, we have Kaplan-Meiers for each of the 5 groups. On the left-hand side, we have our posterior estimate, which is the continuous line, and the dotted line is the maximum likelihood estimator, once we have the partition defined. So our estimator is blue as compared to the estimator that is the Kaplan-Meier, and they all look very, very, very well. And this is the effect of the covariates. Age has no effect in the first 4 groups, and it has a negative effect in the 5th group. Treatment duration has effect on 4 of the 5 groups. Group number 3 has no effect for none of the covariates. But treatment duration has effect in the first 2 and in the last 2 groups. And most of them is a negative effect. And this is it. If you have more questions, I'll be happy to answer. And this is the paper, you can check it. It was published 2002.
So just a couple of slides ago, you had sort of X1 and X2. Is it a partition? So can you go back to that slide? Yeah, one before that, I guess.
This one, yes.
So if I did a scatter plot of age versus treatment duration, well, it's a partition into 5 groups. Is it 5 clusters?
That's right.
And are those regular? I mean, are they contiguous? I mean, does it look sensible, or can you tell?
Unfortunately, I don't have the graph. So we are saying a graph of scatter plot in the 2 covariates to see how they are split into the 5 different groups.
Yeah.
I don't have the graph, and it would be good to have it to see if they are separated. But the thing is that it's not only the covariate effect, it's also the survival time, the observed survival time that is driving the clustering. So it's a combination of the 3 different variables: the covariate effect and the observed survival time that is determining the different clusters.
That's driving the algorithm, but in terms of interpretation, it'd be pretty odd if one cluster was, bottom left and top right of that scatter plot.
In the scatter plot of in the covariate space?
Yeah.
Yes.
Pretty interesting, I guess. And
Yes. I think it would be informative to see that graph. Yeah, unfortunately, I don't have it. I don't remember if it is in the paper, but
Can I ask a follow-up question on that? Or more generally, like outcome guided clustering, right? Essentially, that's what you're doing. You have the outcomes and then you have a bunch of covariates. But from an interpretational perspective, usually folks, based on whatever covariates they have, they do clusterings and then say for gene expression data and then see if that breaks up into prognostic groups.
actually, that was the main idea. So instead of just looking at the difference in the covariates and to do like a pre-selection of the individuals according to a homogeneous covariate space, we are using the information in the covariates as well as in the survival.
Yeah, so that goes to sort of Jeremy's question of the interpretation, right? So when you go that route, you sort of get the interpretation of which similar covariates contribute to survival. Like, can you draw some interpretations with this when you bring in the outcome? In this case, you have 2, but if you had say multiple covariates, which is it an age effect? Is it a treatment effect, or is it something else? Like, how do you parse it up?
Actually, in the ideal world, you can separate and say that this is the covariate that is driving the survival time. But it's usually a combination of covariates. I don't know if in real life it's mainly few of them that drive the output. But here we are combining all of them. And then perhaps here, for instance, in this group 3, there's no covariate effect. So it's only the output of the survival that is determining group 3. It's not the covariates. Yeah, but also I'm also interested, I will look for the graph that you are suggesting.
You can tell a little bit, if you go back to you have a picture.
Yeah.
Every single group, just look at the grey group at the top, right? It covers the whole range of age. And it covers the whole range of treatment.
So that was my question, like, is it older individuals have lower survival or it's just spread out?
There's a whole range, horizontally, there's a whole
Yes,
range
yes,
covered.
yes.
So it doesn't look like it's a particularly neat partition, in fact.
Yes, in the covariate space, yes. So it might be that it's the survival more that is driving the clustering rather than the covariance. The covariance is just like minimal. Yes, no, but definitely the graph you're asking should be very meaningful in interpreting the results. Yes, definitely.
So can you go back to your method, how you determine the optimal number of strata?
Right.
So I'm just wondering, do you see any uncertainty quantification on the number of strata in your method, or you actually just fix that after you determine this? You
No.
just fix that around the MCMC. How can you make sure you keep that number of strata in your method?
Yes, each MCMC output defines a different stratification. And the size of the number of strata is different in each iteration.
Right.
So you take into account that and define this loss function for this value Kn. These are the different groups. So this is changing. But you take into account the different group sizes, the different stratifications here in the definition of the loss. And then you want to minimize this loss. So it's not fixed a priori.
Right, but when you get the optimal stratum, whether if you look at the posterior distribution of this number of strata, I'm wondering how uncertain in your like real data analysis and also in your simulation data analysis.
Yeah, actually, we didn't do that for this particular data, but it is well known that it's normalized random measure pictures. They are the distribution for the number of components. It's a unimodal, and it's usually around the true one when we have a simulation study. And it has uncertainty. Sometimes we choose 1, 2, 3, but it has a very high mode around the true one. So I didn't show that graph, but these kind of models, they are very good for determining the number of components when you have a control setting.
Once you fix that number of groups, how did you summarize this stratum-specific parameters? You actually different MCMC regions you have.
Yes.
How you match them?
There's two options. Okay. So one option is you have the different bunches of MCMCs, and then when you choose a stratification number 7, the run number 17 that has 5 groups. What we do is we fit the model, but only conditionally on the observation in each group. So we estimate the hazard, we use the same model, only for the data in each group. So we do a refitting of the model conditionally on the number of components. And it's not only the number, but it's the stratification. Each individual is assigned to a different group.
You need to refit. You're not summarizing. I see. Okay,
Exactly.
that makes sense.
Yeah, so do you assume the different clusters have the correctly specified kernels, correctly specified regression models? And does that impact how you would derive the strata? Because you have the optimal in there, so I assume it's optimal relative to a particular curve.
That's correct. The optimality is in the number of groups and what groups, but they are conditionally on the kernel unit.
I see.
And then this is conditionally on these 3 kernels. So among the 3 kernels, this is the best result we could provide. But you're right. The kernel, not the 3 kernels, none of them could be good enough for the data.
I see. So the model fits then. So I actually was just discussing with one of my students about this, but on the regression context, I think people are trying to use this kind of approach to do nonlinear predictions. In what sense? So people introduce this clustering mechanism so that after you marginalize out the cluster index, you have a very flexible relationship between the X and Y, right? So I think people would then use that resulting marginalized relationship between one X to do prediction. You give me X, I give you Y, right? So I wonder, I wondered, did you do any kind of model checking, for example, using these predictions, or what kind of model assessments you did with this? I think that probably is relevant to the kernel misspecification.
Yes, we didn't do any model checking, but the typical ones are you do this posterior predictive check.
Yeah.
And you sample from the posterior predictive to see how it compares to the observed data, but we didn't do that here. But I'm thinking about the very nice questions you made, and I have now an answer for that. I will go back to the. No, that was a very good question. Okay. Okay, and now also because you notice this, probably, and you can see the picture here. If we had plotted in the covariate space the colors of the different groups, they will all be mixed. As we can see, the range of the covariates, they covered for the 5 groups, they cover the whole range in the age and in the treatment duration. It's not the covariate space that is itself. We are not partitioning the covariate space. We are partitioning the covariate effect. So for those individuals that are in the same group, the effect of the covariates is the same. So they might not have the same covariate value, but they have the same covariate effect in the survival, which is different.
So where is it useful then here? What have you achieved in this example here? I mean, you put things in 5 groups, right?
Yes.
You just order the times and put them in 5 groups that way. So what are you going to tell these scientists who've collected, clinicians who've collected this data that you've achieved with them?
So you are saying that it might be more useful to split the covariate space, so it's easier to excel.
As an interpretation.
As an interpretation purpose, yes. Yes, no, I agree. No, I agree. This might not be easy to sell to the scientists, especially to the people who are in these treatments, to select. Okay, you belong to this group because you have this age and this treatment duration, then your survival will be of this amount. Yes. Yeah, it's a different kind of stratification. You're right. Might not be easy to sell. Yes.
Can you adapt it so that you'd get more contiguous spaces in your clusters within the covariate space? It's desirable to me.
Yes. I think that not the model M2, which is the more flexible one, but probably M1, when the covariate effect is the same for all individuals. In that case, the groups might be more interpretable in the sense that they are useful in practice. Not model M2. Model M1 perhaps. When the treatment effect is the same, and then in that case, the partition is more by the value of the covariates. Yes.
Thank you for the nice discussions. Thank you, Lucas.
Well, thank you guys for your questions.